Welcome to the 106th video in this series. So this video is the one where at last we're going to implement the multi-threaded or parallel search algorithm into Vice. On the screen here you can see that I've got some output. In preparation for this video I went into UCI.c and just ran on infinite the win at chess 2 until it found the solution. It found the solution after 270 million nodes and nearly a minute of running, so B3, B2, and obviously this was on a single thread. And the reason I wanted to save this was just that when we actually have the multi-threading up and running, I want to check what the scalability is. The way to do that is very simple. It's just to look at how long it takes to reach a solution. Now, I've had a bit of a discussion on the Discord with some people that have much stronger engines than Vice and already have implemented parallel search. And the general consensus seems to be that for 4 threads, you're expecting a speed up of around 2 or 2.1. And for 2 threads, you're expecting a speed up of around 1.5 to 1.6 or something like that. So long as at the end of this, we're in that ballpark, then we know that things are okay. So we'll start things off in defs.h, and what we're going to do is make a new structure, and this structure is going to be used to give a particular search thread some information that it can use to start the search. So I'll type def and struct if I can actually type things correctly. And then what we want inside here then is we want an sboard, and we'll do position, so that'll be the pointer to the position that it's searching. Then we want also some search info as well, so I'll do pointer to info so it knows actually sort of the parameters for the search and things like that. Importantly, of course, it's going to need the hash table, which we've got up here, so it'll have a pointer to the hash table, and this is the thing, remember, that's shared between all of the search threads. The position isn't, but the hash table is. And then some other information as well, so we'll give the thread, actually each thread that's searching, a thread number. It needs to have a depth that it's searching at, and also each time it comes out of its iterative deepening loop, obviously it's going to have a best move. Last but not least, let's give this some kind of name, so I'll call it search worker data. The other thing I want to do is right at the top is just limit to a maximum number of threads as well. So what we've got the max depth here, I'll copy and paste that down and type here max threads and set that to 32. And then down inside the search info structure here, what I want to do also is add in an integer here, which just tells us what number of threads we're going to be using each time we search. And this will actually be changed according then to a UCI option in the engine. So it'll be set to 1 if we want to use 1 thread, 4 if we want to use 4 threads, and so on. Now we've done that, we can get on with the main crux of the code, which is inside search.c. I can warn you in advance, I'm going to do a little bit of pasting of code here. You can find the code on GitHub anyway, because there's quite a bit of code we're going to have to write, and I don't want you to have to suffer watching me type things out slowly, and I think it's more beneficial for you to hear the explanations. The first thing we need to do is include the tinycthread.h at the top of the file, because we're going to be making use of threads. And what we're also going to need to do is store a reference to all of our worker threads that are actually doing the search, so they'll go inside here. Now, if you remember the videos earlier on in the series, the way the search works is the search threads effectively are independent of each other and they just share the hash table. Now, at the moment, at the bottom of the search.c, when we search a position, we drop in and we do the iterative deepening here. We need to modify this now and actually do this iterative deepening for each of the threads that we've got. So they need to independently get hold of some information, which is the starting position and the search info, and then run away and keep searching until they're told to stop. And the only communication they do, let's say, is with the hash table. So what I'm going to do is create a new function, and I'm going to call that function iterative deepen, and that's going to replace effectively search positions. So this function here, iterative deepen, is what each of the individual threads starts doing. Once everything's being set up, which you'll see in a minute, each thread will have some worker data and it will effectively be searching inside this iterative deepen. It's a kind of replacement for the search position. Now, because it's a replacement for search position, what we can actually do is take all of the code out of there and copy it, not delete it, because we need a bit of it later on, and paste it inside iterative deepen, and then we can make some modifications. The first thing is we don't need the best move like this. We need to actually have the worker data best move saved here. And we can also remove this clear for search as well. PV moves, PV num can stay the same. We don't need to ask about the opening book because we're actually searching, which means we don't have a book move if we were using the opening book, so we can remove that. We can remove this as well. For the actual iterative deepening itself, we don't need that best move is equal to no move because that was determined by the opening book, so we can take that off, and we can take this end line off here as well. So I can tab all of that back and I'll remove the iterative deepening from here as well, so everything's a little bit more condensed. And now what we've got is we've got the current depth and a red line because we don't have any info here. Remember that the info is actually inside the worker data structure now. It'll be given to it later on. So we can say for current depth, blah, 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 worker data, info, and depth. So each thread that has its own worker data will have info on it, and it'll know then what depth it's supposed to be searching up to. What I'll do now is remove these alpha beta comments here because we don't need them. So we've got the root depth is equal to the current depth, and then we've got the best score is then alpha minus alpha beta bound, plus alpha beta bound, the current depth. And here we have a problem because we're supposed to have a position that we're sending into here. So what we'll do then is we'll take our worker data and give it the position. We want to send in the search info, and we also want to send in our hash table as well. So our worker data, and I think I called it TT table. Didn't I? Please disappear the red squiggle. Yes, you do. Good. Now we want to know is, have we stopped the search? So do we need to exit? So again, we're using the worker data info inside here. So if it's stopped, then it'll break. And now what we want to do is we want to print things out to the console, but we only want to do that if the current thread number is 0. If it's not 0, then we're not going to print everything. Otherwise, we're going to be printing everything for each of the threads that we're running, which is going to get very, very annoying. So what we'll do then is we'll put a line on here, and we'll just say after this break here that if the worker data thread number is equal to 0, then what we'll do is we'll get the PV line, and then we need to set the worker data best move. So we can say worker data best move is equal to the worker data position PV array. Of course, when we're getting this from here, we need to use the position and the T table as well. So all of this is coming from the worker data, which was given to this particular thread, which is searching. If that happens, then we can actually do the printing of the information to the console, because this is thread 0. It's the one that's going to be printing to the console. I can see I've got some red lines because, again, I need to take the info from the worker data here. And here also, I need to take this as well. So it's worker data and info. The printing of the PV will stay more or less the same. However, again, the worker data position, because we're working from the worker data's position, and that should be all we need to do there, just not forget the squiggly bracket. And that's what we need to do for the iterative deepen. So we send in some search worker data. This will be an individual thread that's running this, and it'll keep running until it hits the info stopped is equal to true. And this info is shared between all of the threads, and it'll exit just as the search position did before. Scroll down a bit now. We need to make some adjustments to the search position. So we're going to keep this best move, but we no longer need any of this information that's here. We do need to clear for the search. Remember, we haven't created any threads yet. This is created from the UCI file. When we start a search, we send in the position, the search info, and the hash table. No threads or anything yet. What we're doing is clearing everything for the search. We're checking if we've got a book move. And then down here inside this, if best move is equal to no move, we can just delete everything out of here. So this is when we don't have a book move, and it's inside here that we actually want to start creating our search workers, so our search threads. To do that, we're going to need a function. So above the search position, I'm going to write a new function, and that function definition is going to be called create search workers. What we'll do is we'll print to the screen some sanity code, let's say. So we'll say that we're creating a certain number of search workers, so we can debug this a little in the console later on and have a look. And then what we want to do is we want to make a for loop inside here. And inside this for loop, what we want to do is we want to set up a worker inside here to actually set up a worker thread and then start it off searching. And we want to set off one for each of the number of threads that we have. Before we do that, let's take the create search workers here and just drop it down inside here so that we can at least send in our position, our info, and our hash table. So what we need now is something inside here, or on line 337 for me, which actually sets up a search worker for us. So above create search workers, I'm going to put another function definition inside here, and this one is going to be called setup worker. Now the code inside here is actually going to be quite similar to what we did with the input thread. So we're going to take in a number, so the thread number, which we have inside the loop down here. We're going to take in a reference to our worker thread, which will actually be a reference to the array that we made at the top here, this sort of fixed, rather nastily coded global array at the top. Scroll back down to find where we are in the code. Here we are. Okay, then we take in the position, the info, and the reference to the hash table. The first thing we need to do, though, is we need to allocate some memory for our worker data. So we'll take our search worker data structure then, and we'll allocate ourselves a piece of memory so that we can put stuff inside there. The next thing we need to do is for our worker data, so the pointer to the memory we've just allocated, the position that we have inside there as well, we need to allocate some memory for that as well, because we're going to make a copy of the position. So here we also then want the size of, and it's the S board inside here. So we're allocating some memory because we're going to copy over our position as well. Once we've done that, then we can copy the current position to search to the worker data that we've just allocated. So we can make a copy of our position so we don't all search and make moves on the same board, which would be a disaster. And then what we can do is we can set up the remaining information. So we set up the reference or pointer to our information, the pointer to the hash table, which is the most crucial thing, and then also give our worker its own thread number so we can see in the console what's going on. And that actually is everything set up. The last thing to do now is just to create the thread and set it searching. The process to actually create the thread and get it searching is more or less identical to what we did with the input thread. If I go back into UCI.C, where are we? Yeah, you can remember that we've got this launch search thread here, and we've got this thread create function from tinyc_thread, and inside here we send in a reference to the thread, we send in the function to actually start everything up, and then we've got this void pointer to the data that we want to send. We're going to do more or less exactly the same thing now. The only problem is we don't have the equivalent of this search position thread. We don't have a function that we can call when we start the thread, which is actually what we need to write now. So that function is going to be called start worker thread. And exactly as the input thread code, we're taking in a void pointer to our data. We know that that information that we're sending in there is our search worker data, or it should be our search worker data. So we can use some typecasting to get that back out so that we can use the information. And then what we're going to do is print to the console that the thread of that particular worker has actually started working. And that we can call the iterative deepen, and we can send our worker data into here. So if I scroll up a bit, we've got the iterative deepen, which will now be taking that worker data. And this is going to be called from setup worker on its own thread. So we've been through the process of creating our worker data, copying the board, sending in a reference to the hash table and the search information, giving it a thread number, and then we will call in a minute this start worker thread, sending in this search worker data here. So on its own thread, it'll start and hopefully print to the console and everything won't crash, and print the thread number, and then start the iterative deepening process on its own, completely separate from the other threads, using the data that we send in. So it'll have its info, depth and everything, and crucially it'll have the transition table, and it'll be searching from its own position that we copied and set up down inside here. Once it's finished, then we can say that the thread has ended as well. Obviously we can take this out later on, we don't need it in the console, but it's usually a good idea to have it. And then what we want to do is we want to say that if the thread that has exited here is thread 0, so this is the one we're kind of using for output to the console, then we'll also print the best move that's currently be found by that particular thread in this case. A quick interjection here. Whilst I was editing this video, I realized with horror that I hadn't actually freed the memory that's been allocated for starting each of the threads. So I've added a line in here which isn't in the video you're watching. Well, it is now because you're watching this, but I have updated the code on GitHub with it. But on this line here, I've put free and worker data here so that we're able to free up the pointer to the data that was allocated once the thread has finished searching. So we've got one last line to do, and that's actually the line to create the thread. So I'll drop that in setup worker down here, the thread create. So we're able to set up our worker, sending in the thread number, the position in our array, which is defined at the top of the file, just to save a reference to that particular thread, the position, the info, and the table, and that's all created from here. What we need to do, of course, is actually call the setup worker function. So we'll call the setup worker function then for each of the threads that we have inside the loop here. So I'll just put that inside there. So we've got the thread number, which will be 0, 1, 2, and onwards. We've got the reference to the array, which is defined at the top of the file with its position defined by our index, and we send in position, the info, and the table. Now that's nearly complete. There's one small little thing to do, which is really, really easy to miss, and that's actually inside search position. So here, when we're inside search position, if we haven't found a book move, We're going to create our search workers. They're going to search, and when the depth has been reached or the time has run out or there's a stop or something like this, they'll have this signal on the info saying info stopped is true. However, we need to wait for all of the threads to exit, otherwise we could end up with some funny problems in the program. So what we're actually going to do is delete this here because we don't need this best move being pointed like this, and I'm going to drop a join in here. So we're actually going to wait at the end of here for all of the threads to finish. Now, if you're thinking, oh my goodness, what happens if the delay is very long? The program is effectively blocked. You might be right, but in reality, obviously, with the amount of nodes per second it's searching, it makes a checkup very, very frequently, and the reality is it's instant. There's no real effect on the program. So now that's been done, the last thing that remains is to actually test the program. So I'm going to open up vice.c, and inside vice.c, I'm going to take the info here and put also info thread num, and I'll set that equal to 1 for now. So we're just searching on one thread because I want to check that the output is coherent with the output that we got before. Of course, setting ptable to 1 is probably not a good idea here. I need the thread number is 1. The dangers of copy and pasting, they're always perilous. Okay, so I'm going to cross everything here and jump over into the terminal. So Vice has compiled without any errors or anything like that, which is rather unexpected. So let's run it UCI, and I'm going to type run, and it should start running the win at chess. Now, even though we haven't actually completed the problem yet and got to the solution, I can already see that the node count at depth 15 is coherent with the output that we had last time. Whilst that's running, if I just switch back to the code and have a look at the output, we can see we've got 1046623 and a score of 60. Going back into the console, we've got 1046623 and a score of 60. So we haven't broken anything by creating just one search thread. And you can see at the top here that we've got create search workers 1 and thread 0 starts. I want to wait till we get the solution just to see how long it takes to get there. Okay, then, so that's taken, in this case, 61.1 seconds to get there at depth of 17. I'll type stop. And we can see that we've got thread 0 ends. That's good. We get the best move, which is also good. Let's just type run again and see what it does. Okay, obviously it gets the best solution straight away. The thread starts and stop. Okay, everything seems okay there. So now we'll come to the big test. It said 61 seconds there to find the solution. Let's drop back into the code. And in vice.c here, I'm going to now fix the number of threads at 4 threads in parallel. Drop back into the terminal. Break out of Vice, clear the screen and recompile. And let's rerun Vice and see what we have. So UCI and run. Does everything break? RUN and enter. No, it's not all breaking, which is good. We've got stuff being printed out, and I can already see we've got to depth 16 quite a bit quicker. The big test will now be the depth 17. We had 61 seconds, so I think anything under sort of 30 seconds will satisfy me that things are running more or less okay. I can already see at the top of the screen that we've got create search workers is 4, and we've already hit depth 17 in 18 seconds there. So we've actually got really good scalability just by sharing the hash table. I can see that the best move is the same, the score is the same, and we've already hit depth 18 by 30 seconds. Let's hit stop there, and let's just hit run again, and obviously we're straight away to depth 18 because we're getting everything out of the hash table. So we've actually got really, really good scalability with the program there, which is really, really pleasing. So I'll break out of that and go back into the code. There's one more thing I'd like to do, and that's just obviously add the option into the UCI options to set the number of threads from the GUI or using the UCI protocol and not hard code them in here. What we'll do is we'll hard code one thread in here like so. So it's always got one thread when it first starts. Then I'm going to drop into UCI.c and scroll all the way down. I think we've got the setting of the hash in megabytes here. We can basically use this, can't we? I think so. I'll copy and paste that. And now we want set option name, and we'll say threads value. I think that's 3 more letters, isn't it? So we'll change the 26 here to a 29. Scan everything in. We can leave MB. The MB, if it's less than 1, then it's going to be set to 1 in this case. It's not megabyte threads, but it doesn't really matter, does it? And in this case here, if it's greater than max threads, then we'll set the number equal to max threads, which was our 32. We'll type out set threads to like so. That's okay. And then what we want to do is we don't want to set the hash table, do we? We actually want to set the info and thread num. So we can put info thread num is equal to MB. And that should be all we need to do actually to be able to change the number of threads. There's one more thing I know I've got in the back of my mind that we do need to remove in the code, and that's in pvtable.c. We need to take out this fixing of the number of hash entries, and I'll comment that out and leave it in. You never know when you might need it later on. So the thing to do now is to jump back in and actually test whether this is working or not. So in the terminal then, recompiling Vice and rerunning Vice. Let's just run Vice. Okay, excellent. We'll do UCI. So we should at the moment, if I remember correctly, be with one thread. So I'm going to type run in here, and we can see that it's creating one search worker and searching away. I'll type stop. And now I want to type set option. I've got to remember the syntax for this. So it's set option, name, threads, and I'll say value 3 here. So we'll do 3 threads. It says setting threads to 3 MB. It doesn't matter about the megabytes. Don't worry about this. And what I'm going to do is just type run and make sure that I get 3 threads started. Yep, we've got 3 threads starting up there. So again, if we type stop here, then we see that the 3 threads are ending, and we also get the best move printed out to the screen. So that actually completes the implementation of LazySMP. It's a very basic and simple implementation, but nevertheless, the scalability that we have out of it is actually really, really good. Now, the scalability we had with WinHS 2 obviously is slightly biased because WinHS is a tactical position. Nevertheless, in preparation for this video, I did some testing with a load of other positions as well, and in general, the scalability seems really, really good, at least compared with other implementations or numbers that I've seen. One of the people on the Discord has been providing me with some good statistics to compare against, and I've done that. And it seems really, really good. So despite the relatively sort of rustical, you would say, or rustic sort of implementation of the threading here, we actually have something in terms of scalability that's really, really good. And I hope that you've had some fun implementing this part of the program, and also maybe you've learned a little bit and maybe understood that threads don't need to be quite as complicated as people often think they are. What we now need to do with Vice before releasing a new version is actually try and improve the evaluation a little bit, so we can actually improve the ELO strength, which would actually justify a new release. But that ends this little part of LazySMP. Thanks very much for bearing with me. Thanks for waiting as well. I have a lot on in my private life with work and things, so sometimes I don't have the time to update the videos regularly. So thank you for the patience and the nice messages, and I'll see you soon when we start trying to improve the strength of the engine.